Let's get started with today's lecture, which we will be talking about the energy. We will talk about the dominant sources of energy and discuss some peak oil production and also the concerns that why it is hard to evaluate the future oil production and how important is coal in domestic energy production. We'll also talk about the environmental effects of coal burning, or we can say that how do the nuclear reactors work and what are some of their advantages and disadvantages. Also, we will talk about the main renewable forms of energy and could solar, wind, hydropower, and other renewables eliminate the need for fossil fuels. We'll discuss the photovoltaic cells and how they work. We'll talk about the biofuels, what are the arguments for and against their use. Let's get started with a case study about the greening Gotham that can now that can New York reach an 80 by 50 goal. So greening Gotham is about New York City has a gritty reputation and it's not known as a world leader in energy conservation. The highest The biggest city in the US, New York, uses more energy than almost any other city. Almost all of it is derived from the oil, natural gas, and nuclear power. So, as a northern city, New York needs about 6 months of uh, heating and 4 months of air conditioning each year for its aging. So often the leaky building stock and it has limited solar potential. At the same time, we can see that the New York City planners they also know that climate change threatens the city with rising sea levels. Also, there are some increased hurricane frequencies, the deep heat waves, and economic instability as a warming climate undermines the agriculture. Also, the transportation, health, and other uh, underpinnings of the city's economic foundations. A serious heat wave can be especially deadly for low income and aging urban residents. Or, in short, we can say if all these threats are to be reduced or averted, New York and other cities have to do their share to cut the greenhouse gas emissions. And they need to do it very soon. Talking about the energy resources, a central energy question in environmental science has long been and will there are a lot of questions that will we run out of the oil or as we all know that oil is our single most important energy source in terms of both the volume consumed and diversity of uses from running those cars, trains, ships, to powering electric generating stations and heating our homes. So, oil produces about 36% of our total energy supply, followed by the natural gas, which is about 26%, and coal constitutes about 20%. So together, all these fossil fuels, they make up about 82% of our energy supply. So nuclear energy is about 8%, biomass and waste incineration is about 4%, and hydropower about 3% make up most of the rest. Wind, solar, geothermal, and other renewable energy forms are growing very fast, but they still make up only about 2% of global energy. So, however, that's twice that were a few years ago. One reason for this distribution is the subsidies that we provide for conventional fuels. In 2013, global subsidies for fossil fuels amounted to about $1.9 trillion or about 600 times the support for wind, solar, and all other alternative energy sources. We all know that we use all this energy to grow and prepare the food, to work at our jobs, and to entertain ourselves. Fossil fuels, oil, gas, and coal, they provide the bulk of this energy. Like we already calculated that was about 82%. They constitute about 82% of the total energy. So these are this table here, it represents the energy usage by computers per year, televisions, or the 100-watt light bulbs that we are using, the 15-watt fluorescent bulbs, the clothes dryer, refrigerator. These are the daily usages and that's the amount of energy that we are using on our daily basis. If we talk about the work, what do we mean by work? What's the actual definition of work? So, work is the application of force over distance, and we measure work in units called joules. So, if we talk about work, that means the work is equal to force times the distance it covers, and the unit of the work is joules. And the energy is the capacity to do work, whereas the power is the rate of energy flow or the rate of work done. For example, 1 watt is 1 joule per second. Fossil fuels, they supply most of our energy, like renewables. For example, if we talk about the renewable sources like hydroelectrics, the wind, solar, biomass, they provide about 11%, and nuclear power supplies provide about 8.4%. So in the 20th century, the rich countries of the world, although they made up less than 5% of the total population, uh, consumed more than half the commercial energy. That situation is now changing. However, rising incomes in China are leading to more energy consumption. China now consumes as much primary energy as all Europe, and 80%, 85% as much as the United States. And because so much of the China's energy comes from coal, it has now passed the United States in total carbon dioxide production. So this graph here, it represents the expected versus observed changes in global installed capacity of wind. That's the graph A here, and this represents the global installed capacity of energy, the solar energy. So this is the wind energy and this is the solar energy. The vertical scale for wind is larger than that for solar. You can see here in the graph. We measure energy in units such as joules and watts. So energy can be measured in many ways. We also talked about the power. So 1 watt power is about 1 joule per second. Let's now talk about the coal burning that releases huge amounts of air pollution. Every year, the roughly 1 billion tons of coal is burned in US, which releases like metric tons of carbon dioxide. This is about half of the industrial carbon dioxide that's released by the United States each year. In addition to the carbon dioxide emission, the coal also contains certain toxic impurities like mercury, arsenic, chromium, and lead, which are released into the air during combustion. So it's possible to make either that gas or liquid fuels out of coal, but these processes are even dirtier and more expensive than burning the coal directly. It has been found that coal use is declining in the US. So recent improvements in the technology have made other choices from gas and oil to wind and solar cheaper than the coal. Coal has lower energy content than oil or gas, so it's a less efficient fuel. At the same time, most of our coal power plants are aging. it's expensive to retreat them to meet new public health standards. The mercury and air toxic standards announced by the Environmental Protection Agency in 2012 will slash the allowable mercury emissions from coal-fired power from these coal-fired power plants. So this was required by 1970 Clean Air Act, but it was delayed for decades by owners of old power plants. They argue that their facilities were about to be closed anyway, and so they shouldn't have to install expensive pollution control equipments. Federal regulations, they are also a part of this decline that has resulted in declining the coal usage in US. Over 45 years later, many of those plants are still in operation and still emitting dangerous pollutants. Talking about the domestic oil supplies, they are limited. The concerns about environmental damage from drilling or oil spills like that of Exxon Valdez in Alaska's Prince William Sound and the Gulf oil spill of 2010, it made the many observers worry about the exploitation in such sensitive areas. So, other US regions with potential for new oil discoveries include the continental shelf on the coast of California and Arctic Ocean and Grand Banks. These are the different figures that represent the global oil reserves by the region. So, proven oil reserves, 12 countries, 7 of them in the greater Middle East, account for about 89% of all known economically recovered oil. So, numbers add to more than 100% due to the rounding. Let's now talk about the deep water drilling that poses many dangers. So, deep ocean oil wells in remote places they pose dangers as the 2010 explosion and sinking of the deep water horizon in the Gulf of Mexico. It showed that most of us had not thought enough much about the dangers of these deep ocean oil wells in remote places until 2010 explosion and sinking of the deep water horizon in the Gulf of Mexico, as you can see here in the figure. So at least 5 million barrels of oil were spilled during the 4 months it took to plug the leak. So the well was being drilled in about 1 mile deep water, but that isn't very deep by current standards. So for the Gulf of Mexico, the current record is held by the Perdidos Bearing, which is drilling in more than 3,000 meters of water and then to a depth of about 6 kilometers below the seafloor. Brazil is drilling a similar depth, about 300 kilometers offshore. This ultra deep deposit, which Brazil estimates could hold about 50 to 100 billion barrels, they could make that country fifth or sixth in the world in oil resources. Talking about the tar sands, they are composed of sand and the shale particles that are coated with bitumen, a viscous mixture of long chain hydrocarbons. Shallow tar sands are excavated and mixed with hot water and steamed to extract the bitumen. For deeper deposits, the superheated steam can be injected to melt the bitumen, which is then pumped to the surface like the liquid crude. So once the oil has been retrieved, it still must be cleaned and refined to be the useful. The United States also has large supplies of unconventional oils like oil shales. They are the fine sedimentary rocks rich in the solid organic material, which is called the kerogen. Like the tar sands, the kerogen can be heated, liquefied, and pumped like liquid crude oil. Oil shale beds up to about 600-meter thick underlie much of Colorado, Utah, and Wyoming Wyoming. So, if these deposits could be extracted at a reasonable price and with acceptable environmental impacts, they might yield equivalent of several trillion barrels of the crude oil. So, these are the natural gas wells in Wyoming's Upper Green River Basin. Talking about the hydraulic fracturing that opens up tight gas resources, we all know that the natural gas leaks are a growing concern these days. So, cracks in the well linings or fractures in rock formations can let gas leak into the groundwater. So there was a study that was carried out by the National Academy of Science, NAS, which found that shallow wells near the gas wells in Pennsylvania and New York had about 17 times as much methane as those from the sites far from the wells. These leaky valves and pipelines, they emit a vast amount of methane. So the spills from these wells, they release a powerful greenhouse gas every year. So no one knows how much gas escapes this way. So there are a lot of estimates that are carried out that about 3 to 8% of gas production may be released, especially at the fracked wells. So some studies they argue that as long as these leaks are unmonitored or unrepaired, they make gas 20 times worse than the coal for our climate. So these fracked gas is expected to supply about two-thirds of our gas supply in coming decades. This fracturing those rock formations, they often disrupt the aquifers, however, and contaminates the water wells. Let's now talk about the nuclear power and hydropower. So today there are about 440 reactors in use if we talk about worldwide. So 104 of them are in the United States. Half of the US plants are like 52 or over 30 years old and are approaching the end of their expected operational uh, life. So cracking pipes, leaking walls, and other parts, they increasingly require repair of replacement as a plant ages. The nuclear power now amounts to about 8% of US energy supply. It has been found that rapidly increasing construction costs, safety concerns, and the difficulty of finding the permanent storage sites for radioactive waste have made nuclear energy less attractive than the promoters, which are expected in 1950s. So, of the 140 reactors on order in 1975, 100 were cancelled. The costs of demolishing a worn out plant may be 10 times as much as building in the new ones. So, nuclear reactors have been shut down in the United States, and deconstruction of most of them is now underway. There are some plants, although these plants they are generally small, their costs have averaged several $100 million each year. The nuclear power industry has been campaigning for greater acceptance. They argue that reactors don't release the greenhouse gases during ordinary operation of the reactor. On the other hand, the mining, processing, and shipping of nuclear fuel, together with decommissioning of old reactors and perpetual storage of the wastes, they produced a substantial amount of carbon dioxide emissions and also the other pollutants which are released into the environment. How do the nuclear reactors work? So, radioactive uranium atoms are unstable, and when they are struck by a high energy neutron, So this is the uranium and this is the neutron. When this uranium, that's the radioactive uranium, is struck by a high energy neutron, they undergo the nuclear fission. That means the splitting, releasing energy and more neutrons, causing a self sustaining chain reactions. So this is the pressurized water nuclear reactor, the figure here. So these are the different steps that are carried out in this water nuclear reactor. So water gets superheated and pressurized as it flows through the reactor core. The heat is transferred to non-pressurized water in the steam generator, which drives the turbines to produce the electricity. So the fuel rods, they contain uranium about 235, uranium 235, which are placed in water in the reactor core. So when the control rods are raised, a chain reaction of nuclear fission, like we already talked about, that means the neutrons they stuck that the uranium 235. So a chain reaction of nuclear fission occurs in the fuel rods, creating the heat. The high pressure, that's the superheated water, flows to a heat exchanger, which generates steam in a separate secondary loop. And then the fourth step, the steam turns the turbine, which turns the electricity generator. And finally, the cooling water condenses that steam to water, which returns to the heat exchanger. So this is the cooling tower here. There are certain nuclear disasters that can happen. So, on one scenario is the March 11, 2011 Tokyo time. So, on Friday, March 11 to 2011, a magnitude of about 9.0 earthquake hit the northern Japan, the largest earthquake in Japan's recorded history, which damaged the buildings and roads in its own right. But even worse, it generated was the tsunami waves to about 30 meter high that crushed those buildings, the toppled wall lines, and washed away all the cars, the boats, and millions of tons of debris. So authorities they report that about 15,846 deaths and 6,000 injuries and 3,350 people were missing and 125,000 buildings were damaged by that tsunami or they were destroyed by those waves. So perhaps the worst result of this catastrophe was the destruction of four of the six nuclear reactors that was at Fukushima Daiichi Power Station, 170 miles north of Tokyo. The reactors were shut down as they were designed to do when the earthquake hit, but that eliminated the electricity that needed to pump that cooling water through the intensely hot reactor core. So, backup operators and connections to the regional power grid would have provided emergency power. They were destroyed by the tsunami. The reactors they quickly overheated and the fuel rods began to melt in three of the six reactor cores. Hydrogen explosions in the reactor building at the complex it destroyed all the roofs, walls and scattered all the radioactive debris around the area. So in addition, the spent fuel rods in storage pools of two units also overheated and caught that fire, releasing even more radiation. There were certain plant operators that sprayed the seawater onto the reactors to cool those reactors and put out those fires, but that washed away the radioactive pollution into the ocean and also contaminated the seafood on which the Japan mostly depends. So in 2012, Japan began tunneling under the nuclear complex. What they did was they installed a giant concrete diaper to try to contain those radioactive drainage from the site. So high radioactivity caused the authorities to order evacuation of about 140,000 people living within a 12-mile radius around that facility. But the toll could have been worse if the melting fuel and fires had not been contained. The radiation it released could have been 10 times greater than 1986 disaster at Chernobyl in Ukraine. So this was one of the worst nuclear disasters in 2011. Let's now talk about the water, the power resources. So, moving water is one of our oldest power sources. Many countries produce most of their electricity from falling water. Norway, for example, depends on the hydropower for about 99% of its electricity. Brazil, on the other hand, the New Zealand and Switzerland all produce at least three-quarters of their electricity with water power. If we talk about the Canada is the world's leading power producer or hydroelectricity, running 400 power stations with a combined capacity of about 60,000 megawatts. First Nations people protest, however, that their rivers are being diverted and lands flooded to generate electricity, most of which is sold to the United States. The invention of water turbines in the 19th century greatly increased the efficiency of electricity that produce those hydropower that's producing those hydropower dams. By 1925, falling water generated about 40% of the world's electric power. Since then, that hydroelectric production capacity has grown about 15 times. But there is still fossil fuel use that has risen much faster. So, water is now only one quarter of total electrical generation. Let's now talk about the energy efficiency and conservation. Uh, it's often said that the cheapest form of energy is the conservation. This is why the New York City, that we had the opening case study, is focusing on building efficiency first, even before it starts spending money on new energy sources. So, conservation can save money as well as reduce our energy footprint. So, better sealing of doors and windows can be inexpensive and make your house or apartment much more comfortable. And also, reducing the hot water consumption and remembering to turn off the lights usually cost nothing and lower energy bills. There are countless steps each of us can take that cost nothing and save money as well as energy. The energy cost can depend on how you calculate them. For example, the light bulb efficiency is a familiar example. The cost of 60-watt incandescent bulb has long been very low, often $1 per bulb. So a compact fluorescent bulb that produces about the same amount of light might be 5 or 10 times that. A newer LED light emitting bulb is around $10 depending on what kind of bulb you buy and where you buy it. So, but over a year of use, the cheapest bulb costs 10 times more to operate. Over 10 years, the cost difference multiplies. So, because these incandescent bulbs put such a high demand on communities' energy resources, and because they are responsible for very high energy greenhouse gas emissions, they are being phased out in many places. We have certain LED lights or compact fluorescent light bulbs that are also much safer because they are less hot and less likely to start a fire when unattended than those incandescent bulbs. Conservation involves nothing but the technology innovation as well as changes in your behavior, but we have met these challenges in the past. High energy, high efficiency automobiles are now available. Low emission hybrid gas electric vehicles get up to about 72 miles per gallon, and walking, biking, or taking public transport, they can lower your personal energy footprint far more. So, what we want to discuss here is that it all depends on the costs that we get. It depends on how you use those all these energy resources. Passive housing is becoming standard in some areas. So Germany has long been a leader in energy innovation and efficiency. There are many regions in Germany that have begun to require that new buildings conform to the passive house standards. These standards, they are strict energy use limits along with the guidelines for building practices that reduce the energy consumption to just about 10% of what the normal buildings use. So, in the United States, there are certain incentives such as the faster permitting or tax breaks that can break the tax breaks to building projects that meet the passive standards. They are increasingly very common. So, what actually does the passive housing involve? The main principles are these. So, no thermal bridges, that means the wood or metal components that conduct heat through the walls, roof, or foundation. The second one is the roof and wall insulation, about 24 to 32 centimeters, that means about 10 to 14 inches thick. The third one is the well sealed windows and doors to prevent the heat loss or gain. Also, the heat exchangers that can warm or cool the fresh air as it's exchanged with the stale air leaving the building. There are certain triple pan windows that reduce the radioactive heat loss or gain. Windows are positioned to let in the daylight. So these are some of the main principles that help in this passive housing. Let's now talk about the wind and solar energy. It has been found just a few years ago that this plan would have seemed audacious, but increasingly it appears readily achievable. So, a 2014 report found that US utility scale solar costs are little as 5.6% per kilowatt hour as compared to the gas, which is about 6.7%, and coal about 6.6 cents. The wind has best of all that 1.4 cents per kilowatt hour. Analysts in 2010 didn't expect these prices for wind and solar until 2020. So, and renewables don't have the external costs of like pollution, the health impacts, and price volatility of fossil fuels. So, using only those sites where energy facilities are socially, economically, and politically acceptable, there are more than enough renewable energy from the sun, wind, geothermal, biomass, and other sources to meet all those present energy needs. Wind power is the world's fastest growing energy source. If we talk about the China, which is the world's largest producer of wind turbines, has the second largest installed wind capacity after the Europe. Clean technology provides more than about 1 million jobs in China, manufacturing equipment for domestic use and also for the export. So China now has over 63 gigawatts of wind power, or about one quarter of the world total energy. Wind power could replace all the commercial energy we now use, and if we choose to develop it. So, if you include the land required for mining, wind power takes about one third as much area and creates about five times as many jobs to create the most same amount of electrical energy as coal. You can see here. So, it's almost the same. So same types of jobs, same increase in jobs, and also creates the same amount of energy as coal if we use the wind energy. Wind power provides the local control of energy. The cooperatives, they are springing up to help landowners and communities to finance, build, and operate their own wind generators. So, about 20 Native American tribes, for example, they have formed a coalition to study the wind power. Together, their reservations, which are in the windiest, less productive parts of the Great Plains, could generate at least 350 gigawatts of electrical power, equivalent to about half of the current total US installed electrical capacity. Let's now talk about the photovoltaic cells that generate the electricity directly. So, what actually these photovoltaic PV cells are? They actually capture the solar energy and convert it directly to electric current by separating the electrons from their parent atoms and accelerating them across a one-way electrostatic barrier that's formed by the junction between two different types of semiconductor materials. So the source is the sunlight, and these are the phosphorus enriched n-type layers you can see here. So you can see here the first step in this is that the photons, they strike the panel surface, that's to excite the electrons which move to the lower layer of panel. And then in the second step, a shortage of electrons results in the surface layer, while an excess of electrons develops in the lower layer. Third step is the wires that connect the two layers allow electrons to return to the surface layer, creating an electric current, like you can see here, that helps to lighten the bulb. So this is how these photovoltaic cells they work. Let's now talk about the biomass and geothermal energy. The plants, they capture immense amounts of solar energy by storing it in the chemical bonds of the plant cells. Firewood is probably our first fuel source. So, for more than a billion people in developing countries, burning biomass remains the principal energy source for heating and cooking. So it has been estimated that about an estimated 1,500 meters of fuel wood is gathered each year globally, which amounts about half of all wood harvested. So wood gathering and charcoal burning, they are important causes of deforestation in many rural areas. And providing efficient wood stores can improve the people's lives while also saving those forests. Ethanol has been the main focus. The biofuels, ethanol and biodiesel, are by far the biggest recent news in biomass energy. Globally, the production of these two fuels is booming from Brazil to Southeast Asia. So, one fifth of the corn, or we can say the maize crop, currently is used to make that ethanol. Oils from crops such as soybean, sunflower seed, rapeseed, and palm oil fruits, they are relatively easy to make into the biodiesel, and many need only the minimal cleaning for use in the standard diesel engines. There is an alternative, that's the cellulosic ethanol. So far, there are no commercial scale cellulosic ethanol factories that operate in North America, but the Department of Energy has provided about $385 million grants for six cellulosic biorefinery plants. These pilot projects will test a wide variety of feedstocks, including the rice and wheat straw, the milo stubble, the switchgrass hay, almond hulls, corn stover, and wood chips. So, a number of techniques have been proposed for extracting the sugars from cellulosic materials. Most involve the mechanical chopping or shredding, which is followed by the treatment with bacteria or fungi to break down those cellulose into the soluble sugars. The methane emission from the biomass is efficient and clean. The main byproduct of this digestion, that's the methane, has no oxygen atoms because no oxygen was available in digestion. But this molecule, it oxidizes or burns easily, producing carbon dioxide and water. And consequently, the methane is a relatively clean, efficient fuel. So burning these methane is efficient and clean burning molecule which oxidize these easily. So concerns about the greenhouse gases may lead to the further development. Let's not talk about the algae. Can they be a future hope for the future? So algae might be an even more productive biofuel crop than they are discussed so far. So while miscanthus can yield to about 13,000 liters of ethanol per hectare, some algal species they grow in a photobioreactor, that's the high-tech greenhouse. They might theoretically produce about 30 times as much high quality oil. So this is partly because the single celled algae can grow about 30 times as fast as higher plants. So furthermore, some algae they store about half of their total mass as the oil. So researchers they have found certain strains of algae that grow rapidly under hot and saline conditions, producing those lipids or oils that could be converted to the biodiesel. One of the most intrinsic benefits of algal growth facilities is that they could be placed next to the conventional power plants where the carbon dioxide from burning either the fossil fuels or the biomass that can be captured and used for the growth of those algae. The Earth's internal temperature can provide a useful source of energy in some places. There are certain high pressure, high temperature steam fields that exist below the Earth's surface, and around the edges of continental plates or where the Earth's crust overlays the magma, that's the molten rock, which is close to the surface. This geothermal energy is expressed in the form of certain hot springs, the geysers, and fumaroles. Like we have already discussed, the Yellowstone National Park, which is the largest geothermal region in the United States. Iceland, Japan, and New Zealand also have high concentrations of those geothermal springs and the vents. Iceland also has ambitious plans to be the first carbon neutral country, largely because the Earth's heat provides steam for heat and electric energy. Geothermal heat pumps can heat and cool efficiently, uh, they can cut the heating and cooling costs by half in many areas. In summer, warm water is pumped through buried tubbing, that's the earth loops, where it's cooled by constant underground temperatures. And in winter, the system reverses and relatively warm soil helps the house, as you can see here. So these are the basement heat pumps. So pumping fluids through deeply buried pipes can exchange the temperatures with the soil to efficiently heat or cool your home. So this is about the geothermal heat pumps. So what does an energy transition look like? Fuel cells provide direct current electricity as long as they are supplied with hydrogen or oxygen. For most uses, oxygen is provided by the ambient air. Hydrogen, on the other hand, can be supplied as a pure gas, but hydrogen gas is difficult to store and is highly explosive. So it's more common to strip that hydrogen atoms from fuels such as natural gas, methanol, or we can talk about the ammonia, gasoline, ethanol, or even vegetable oils. So even methane effluents from landfills and wastewater treatment plants can be used as a fuel source. So depending on the environmental costs of the input fuels or fuel cells that can be a clean energy source for office buildings, hospitals, or even the homes. So fuel cells, they are actually the devices that use the ongoing electrochemical reactions to produce an electric current. They resemble the batteries, except that they are recharged by adding a fuel or a source of hydrogen atoms, while a battery is recharged by adding the electric current. What's our energy future? So, could we get all our electricity from the renewable, environmental friendly resources? Or Mark Jacobson from Stanford University and Mark Dalucci from the University of California, Davis, they believe that we can. They calculate the currently available water, wind, and solar technologies. They could supply about 100% of world's energy by 2030 and completely eliminate all our use of fossil fuels, thus reducing the greenhouse gas emissions and global climate change, which is the main cause of warming our climate. So here is a renewable energy scenario for 2050. Cogeneration would mostly burn the natural gases to generate both electricity and space heating. The World Energy Council projects that renewables could provide about 60% of world cumulative energy consumption in 2030. So here is the breaking percentage of these, like for example, the onshore wind will constitute about 30.92%, and these PVs will provide about 37%. The tidal ones, hydroelectric, will be 3%, and tidal will be like 0.1 for waves, 0.37, and geothermal 1.25%. So this is the energy renewable energy scenario for 2050. So in short, we can say that if is there enough clean energy to meet our needs? Yes, there is. So let's conclude today's chapter. We talk about the fossil fuels like coal, oil, and natural gas that remains our dominant energy sources, but oil is being depleted and coal causes environmental damage. So natural gas is abundant and cleaner than the coal, but fracking, the most common method for extracting natural gas, may release so much methane into the atmosphere. There are certain nuclear power that doesn't create carbon dioxide while operating, but storage of waste is a problem. So, rapid innovations in solar, wind, wave power, and other renewable energy sources now make it possible to get all of our energy from clean technologies. That was all about today's uh, lecture. Thank you.